Okay, welcome everybody. Good morning, Engineering 201, Engineering Mechanics, Lecture 7, okay, summer section. So one more week, we're starting one more week. Before the announcements and a few things we have to discuss, let's pray. In the name of Father, Son, Holy Spirit, amen. Direct the Lord, beseech you our actions by holy inspirations, and carry them on by grace's assistance, that every prayer and work of ours may begin always from you, and through you come to completion, through Christ our Lord. Amen. Father, Son, Holy Spirit. Amen. Okay, guys. So I hope you guys have a great weekend. Ready for one more week. Here we approaching half of the summer section. Okay, this semester, if we can say like that. Um, and a few things. Okay, a few things really important. Next week, meaning Tuesday next week, 1 week from now, is our midterm exam. Okay, our midterm exam. And my lecture one already explained how we're going to do. I'm going to use the Brightspace platform to provide you some questions where you going to have some time to finish those questions. Each question you should scan and upload the answer and then move on to the next question. Okay. Um, so in order to do that, I will probably today prepare like a fake midterm exam over there, like the quizzes, and then I'm gonna open for you to at least to get familiar with the platform and how it's going to do, how you're going to do during the test. Okay, it's not gonna count any point. If you want to take it, you can take it. Just put like random questions, or I'm gonna put the homework questions over there. So just for you to practice to see the question, upload the answer, move to the other question, get familiar where you're gonna see the time running. Okay, so pretty much like that. Uh, the test will be Tuesday, the whole Tuesday. You can take the test. You can take the morning, you can take the afternoon, but once you start the test, you're gonna have probably around 3 hours to finish the test. Okay, and of course, I have to take on Tuesday. So I'll mail you guys once again today. But if you are watching the recorded lecture, please make sure you have time on Tuesday to do the test. Okay, I already told you this on lecture one. You agree? Okay, all of you agree. I didn't have received any answer about that, or any questions. So looks like everybody agree on that. Okay, you have to take it on Tuesday next week. Okay. Um, Everything that we cover so far, first week, second week, is going to be in the test, plus today's lecture. Okay, so lecture 7 is going to be on the test. Okay, tomorrow we're going to start a new thing. Tomorrow is not going to be on the test. Okay, it's going to be in the final exam. But today's lecture, lecture 7, is going to be on the final, on the midterm exam. Sounds good? Um, on Thursday, I'm gonna bring more problems and review every single concept and every single knowledge that we got from these first few lectures, and also do a little bit more problems. And you can also bring me questions regarding homeworks and any other questions, problems solved during the class. Okay, you can ask homeworks today as well. Okay, no problem. Uh, and to finalize, okay, to finalize my announcements, I already grade homework number 2. So if you submit, you receive a grade. Okay, I already posed the solution for homework number 2, so you can finish the class, the lecture, and go and check your answers with my solution key. Um, and also, I post homework number 3. So homework number 3, I believe the first 4 questions. The first 4 questions, they are regarding lecture 7, this lecture today. So we have 4 more questions for you to practice and also submit your answers, okay, during this weekend or during this week. Um, so you can study for the midterm. Okay, the homework 3 also has 2 questions regarding the topic that we're going to cover tomorrow, but they are not going to be in the test. But I want to already solve homework about it. If not, it's going to be in too many weeks beyond in front. So we're gonna lose like the time. Okay, but that's it. Okay, that's it. If you have any questions, please let me know. Email me. Okay, but next week, Tuesday, you can take the test. All right. For those who are here live, any questions regarding it? So Thursday review. Okay, Thursday is going to be review. We're going to review everything, homeworks, questions. I will bring more different questions and so forth. And please expect to at least to practice with a fake exam that I will post today. All good? Okay. Yes. All right. It's taking time to share the screen. Okay. So let's jump to lecture 7. Okay. End of announcements. Let's jump to lecture 7, new lecture. And once again, this lecture is going to be on the midterm. Okay, so this is an important lecture just to wrap up those last 2 weeks that we have been together. Okay, guys. So we have been talking about 2-dimension, 3-dimension moments. Oh, sorry. Equilibrium. I'm still able to submit homework too late. Yeah, you can submit it. Of course, I'll discount some points because I already post the solution. Okay, so you can still submit to get some of the points back. All right. So to the equilibrium of a rigid body. So we have been talking about 2D and 3 dimensions. Okay, and most of them force, force, and then this last week we talked about moments. Okay, and we also talk about 2D and 3-dimension equilibrium of a particle. Okay, of a particle, meaning we have a point, and that point we have the force acting on that particle. Okay, and then last week I introduced the moments. Okay, moments where we have a rigid body, and that moment, and that a force we cause this body to rotate with respect to a point, with respect to an axis. Okay, but now let's bring all those together. Okay, how we find equilibrium in a rigid body. Okay, we talk about equilibrium in a particle where we have like, tension, and a force. How much should be the tension so that particle to be in equilibrium? Now we're going to talk about body. Okay, we have a beam, we have airplane, we have human body, we have a computer, we have a table. Okay, how we keep it, those objects that has length. Okay, that the size is going to matter for us. Okay, because now we could have some moments how we maintain the equilibrium for those rigid bodies. Okay, so for a rigid body, okay, the condition of static equilibrium means that the body under analysis do not translate or rotate under given loads that act on the body. Okay, so what is equilibrium? We have the force, okay, that we already know. The force should be zero. Okay, should be in equilibrium, not moving. Okay, but also now we have one thing more. The moments should be zero, meaning there is no translation or no rotation. Okay, uh, caused by the force, but the whole force, every single force on that body. Okay, it means that the resultant of all the force act on a rigid body is 0. Okay, same thing that we have been working so far last week. Equilibrium of a particle, sum of the force equal to 0. Same thing here, sum of the force should be 0. But now, the moment about any point sums to 0. Okay, meaning any point that I take in that rigid body, once I calculate the moment about that point, in any point of the rigid body, it should be 0. Okay, and we're gonna work with 2 dimensions, meaning that, okay, let's bring the equations back. Sum of the force in x should be 0. Sum of the force in y should be 0. Okay, so those 2 equations we have been working, we already work with problems, okay, when we were talking about a particle. But now, what do we have? Sum of the moments about a point should be 0. Which point, Bruno? Which point is this moment point, this point O? Okay, any point. Okay, so any point that I pick on my rigid body, once I calculate the moments, it should be 0. Okay, should be 0. Now, guys, before we start solving problems, think about, okay, think about to have this calculator, my calculator right here. Okay, and then what's going to happen once I apply the force? Okay, if I don't have anything to hold it, once I apply the force, what's going to happen? I was going to rotate. Okay, so I just said that for to be in equilibrium, okay, there is no rotation, no translation, no force acting, okay, no moving, no movement. Okay, so what I need to do, I need to have some support, some grip here. Okay, so something is gonna hold this calculator. So once I apply the force, okay, the calculator will not move. Okay, will not move. Same thing that, for example, you cannot see here, but I have my table here where my computer is. I have the computer, I have my second screen here, I have all my objects, I have my weight here on my table. And why this part of the table, the top of the table is not going down? Why? Because we have legs of the table. Okay? We have legs of the table. And what their legs are doing, once I am applying this force, what their legs are doing, they're kind of fighting back. Okay? Hey, the legs are talking to each other. Hey, Bruno is trying to push us. Okay? And go down. However, legs, let's put together and let's support the table. So the table will keep the same position, even though we have the weight on top of the table. Okay? And what are those legs? Okay, what do we call? We call supports. Okay, so for those equilibrium equations and 2 dimension, not 2 dimension, sorry, and the rigid body, 2 dimension, 3 dimensions, okay, we have what we call support. And those supports, they're gonna cause some reactions. Okay, action, reaction. Well, if I have my weight on the table, as I said, the legs are gonna work. They're gonna react my force. I put some force down, they're gonna react to it. I'm gonna put some force up. So it's gonna be kind of a fight. Myself pushing it down and the legs pushing up. Okay? So that's what we have in those problems. In order to maintain the equilibrium in 2 dimensions or 3 dimensions or rigid body, okay, we have some supports. Okay, some supports. For example, the beams. The beam is right there. Okay, and what's giving support to the beams? Most of the time, columns. Okay, the airplane. What is giving the support to airplane when he's down on the road on the airport? Well, the wheels. Okay, same thing for cars. All right. So we have some support. Okay, If I take, we're gonna have probably time to do a problem here. I don't have my, but if I take a ball, a weight, and I'm holding this ball, okay? Why is keeping my arm to not going down? Well, it's the force that I'm doing, but who is doing this force? Is a reaction against this weight of the ball with my muscle, okay? My arm here, muscle, tendon, okay? So we have some reactions, support reactions, that we call support reactions. So depending of the support, they're gonna give different reactions. Okay, depending on the support, it's gonna give different reactions. Some of them, okay, some of the reactions gonna prevent translation. Okay, prevent translation. Another is gonna prevent rotation. Okay, some of them are gonna prevent you move right, left, up, and down. Some of them are gonna prevent rotation. Rotate to clockwise, counterclockwise, both directions. Okay. So our job when we start those kind of problems today, first thing we need to figure it out, what are the support reactions, or what kind of support I have, and which reactions that support will bring to the problem. Okay. For example, I have here a list for one of the most commons that we're going to find. Okay. For example, let me go here with you. This first one. Okay, sometimes we can have this light cable, okay, or a link. Okay, this link. And what are the reactions that we have? Well, we're gonna have a reaction, okay, right here. That link is just one unknown. The reaction is a force that acts in the direction of the cable or the link. Okay, that's pretty much what we had in the particles. Okay, we have cables, and we call that reaction, we call what? Tension. Okay, so the cables are gonna bring tension, and that's what we did. The tension here, okay, is gonna hold that one in order to not to move. Okay, so that's pretty much what we did in particles. However, we can have in rigid body as well. We can have just cables holding, okay, a structure. For example, you see, I don't know, when you go to some structures, gonna go to other place, that is what? A structure being held by cables. Okay, that's common. Okay, we have cables, and those cables are bring some reactions. They are doing some force. Okay. Now, the second type of connection that we can have that's very common, especially for you guys who are civil engineering and mechanical engineers, rollers. Okay, rollers is very common, and is one of the most common that we're gonna work in this class. What is the roller, or rocker as well? Okay, those bring one unknown, just one unknown. Meaning we have just one reaction. The reaction is a force that is acts perpendicular to the surface at the point of contact. Okay, meaning this roller is doing some force in order that the beam or my body on top of it will not move, okay, down. Sometimes also close, not moving up. Okay. However, if I move then right and left, this will move because there is no restriction on the x direction, left and right. The only restriction that we have is what? Up and down. Think about this as a skateboard. Okay, looks like a skateboard. Okay, so we can move left and right, but the skateboard is still, at least, is restricting the movement going down. Okay, keep the skateboard over there. Okay, so roller. Okay, and I don't know if you pass once you're driving. If you're driving around, you're in the 95 here. Okay, when you pass below under a bridge, okay, take a look at the supports. Sometimes the older one, you're gonna see something like that. Okay, a few more. Okay, let's just go a little bit faster here. Okay, we can have just the smooth contact surface, meaning it's just on the ground. Okay, the ground is giving the support. Okay, that's one unknown as well. And the last one we have here as well. Okay, is smooth pin connect color. Okay, this allows us once again to move left and right. It can move. It can rotate as well. Okay, it can rotate. However, this movement is restricted. So it gives us just one reaction. Okay, so those F here, okay, those F are the reactions. Okay, reactions. Okay, what the support is introducing to the problem. Okay, so I didn't mention here, sorry, but the roller once again can go left and right, and also can rotate. Okay, I can rotate this. Okay, can rotate. Think about this, my arm. Okay, I can rotate. Okay, kind of a pin connection. Think about a pin. Okay, I have a bolt here. What happened with the bolt? The bolt, you can rotate. Okay, you can rotate as well. Okay, this is the roller. Now, what are others? Okay, and essentially I said about pin, but just to show you how is the rotation for the roller. But what is a pin connection is really this number 5, which is kind of a bolt. This is truly a bolt or a pin connection, okay? Because it can also rotate, but think about it, once we have the bolt, we cannot move left and right. We cannot move up and down. So this movement and this movement, they are restricted. If they are restricted, if I cannot move left and right or up and down, I have now two unknowns. Okay, two reactions. However, I can still rotate it. Okay, I can still rotate it. Okay, so this is also a very common one that we're going to use a lot here in this class. Okay, the last two here. First one, slider 60 slider fixed connected collar. So this is very common, probably in your house when you have like this slide door or sliding door. Okay, I have here because of my background, you're not going to be able to see. But what happened? Once you slide, you can slide what? You can slide left and right. Okay, if this is rotate, let's think about this rotate. But let's talk about this one. You can slide this up and down for this one. Okay, but you cannot move like this because it's fixed here, and you cannot rotate. It will not rotate. So once we have those two, okay, we have two reactions. However, one reaction is the force and one reaction is the moment. So Bruno, can we have moment reaction? Yes. If this does not allow us to rotate, then he's fighting against the moment. So it's reacting the moment. So we have a moment reaction. Okay. And then for finalizing, we have number 7. That's the fixed support. For those who are a civil engineering, maybe mechanical engineering, you're going to see as well. Those are what we call, like these as well, cantilever beam. Very common. Cantilever beam. It's just a beam fixed on the wall. Okay? And we have for this one 3 reactions because we cannot move left and right. We cannot move up and down. And also we cannot rotate. There is no rotation at that point. Okay? And those reactions I'm talking about, okay, I'm talking about at the point where we have the support, okay? Support reactions. Of course, if we have a force here, of course, this part is going to rotate, it's going to move. But I'm talking about the support, okay? The reactions at the supports, okay? So we're going to have three unknowns, meaning three reactions, okay? So those supports, they're going to be important in our problems, okay? And maybe you're confused a little bit right now, but we're going to solve some problems, we're going to figure it out. But the supports are a big part of today's lecture, okay? Well, I just want to state once again here, because we mentioned free body diagram already, but most of the times, okay, in order to visualize what the supports are doing and what they're bringing to the table, is a good idea, very good to draw the free body diagram, so you can remove all the noise and just put there the reactions, the force, and see what we can do to solve the problem. Okay. Sometimes we also able to break the problem into components, so we can find reactions in different ways. Okay, so free body diagram, very important once again for us here on those problems. And to finalize, I just want to mention as well, okay, weight and center of gravity. Okay, when the body is uniform or made from same material, the center of gravity will be located at the body's geometric center. Okay? Meaning, some problems we're gonna work, let's say this is a box, and that box is gonna have a weight. Okay? The same way that we mentioned in few problems, in few lectures ago, we have weight of the objects. Okay, some of the problems are going to ask us to consider the weight, and what are we going to have? We're going to do, well, we're going to apply that weight. Now it's not going to just one point, it's a body, it's a box, it's a car. We're going to apply that weight, okay, at the center of gravity. Okay, so this point G. Okay, if it is uniform material, it's going to be right in the middle. Okay, right where the body's geometric center is. If it is not unusual shape, the location of this G point is going to be given to you. Okay, but you know that, hey, all my weight will be applied on that center of gravity with respect to equilibrium equations. Okay, and to finalize, one more thing, just example here to prepare us to the problems that's coming. Idealize models. Okay, we as engineering, what do we do? We idealize a lot of things. Okay, we have to have the ability to model, idealize structures, supports, and connections. Okay, for example, we are seeing this, let's say, let me use the word beam with other trusses here. Trusses, let's say, okay, if you're not familiar, let's say there's a beam and also those are other three beams. Okay, if you're not familiar. And what this is happening, what is happening here? For example, B, as you can see here, this beam AB is just on top of this, probably this wall. Okay, and this wall is just giving support in a y direction. Okay, meaning we can have this B just one unknown, meaning this one. Okay, so right here I have one reaction, just one reaction. But once we take a look at this one here, my beam is also on top of a wall. But looking here, okay, we have this part with not is not gonna allow the beam moving to the left. Okay, so it's gonna give some support, okay, here and here. Okay, we're gonna have two unknowns. Okay, right there. So what we are doing, we are idealizing those supports. We idealize that this is going to be a pin connection, and we idealize that B is going to be a roller connection in order to analyze the problem. So that's what we do. We idealize models. Okay. Same for those trusses. Okay, we are going to learn that those trusses, they are putting some force here. Force, force. So what I'm going to do? Force, force, force. And this is the structure that I'm going to analyze. I'm going to analyze what's happening with this structure. But in reality, what I'm from where this is coming from? It's coming from a situation like this. Okay. So just to show you that, okay, I'm going to show you some drawings, but always there is some link with a real problem. Okay. It's not like just throw some problem over there. Okay. There is a link. We analyze models. Okay. There is a link how we are doing this with the real world problems. Okay. Because sometimes you're not gonna see like using like those kind of figures, but once you see these, it's just the idealized problem. Okay, let's jump to the problems, put numbers, and maybe it's gonna be easier to follow. Okay, let's solve together problem number 1. Let's see what's going on here. Any questions so far? Those who are watching, all good. If you have any questions, if you are watching the recorded lecture, please type in the comments or mail me. So let's jump to it. Example number 1. Determine the horizontal and vertical components of reaction on the beam caused by the pin at B and the roller at A. And let's not consider the weight of the beam. Okay. So for example, for this one, the problem is asking, okay, let's not forget about the weight of the beam. Let's work just with the force that are there. Okay, that sounds good. Okay. So first thing that we have to do, okay, let's analyze this problem. Well, I have 6 Newton inclined force. With that, probably I have to find the components. Okay, and then D, B here, all of them in the vertical, so I should be good. Now let me take a look at the supports, because it was mentioned that A is a roller. Roller, okay, if you go there, rollers, right here, rollers, okay, give one reaction. And the reaction is a force that acts perpendicular to the surface. Okay, so reaction perpendicular to the surface, I'm talking about this reaction right here. Okay, let's say AY. Okay, and B is a pin. Pin, that's the go there, pin right here is smooth pin. Two unknowns. The reaction are two force components, Fx, Fy. Well, then right here, okay, perpendicular to the surface, By, and right here, X, Px. Okay, actually, let me put it like this. Oh, sometimes the students get confused. So let me put the Bx here, positive, going to to the right. Okay. All right. So it looks like I have this kind of problem. So let me write the free body diagram. Free body diagram. Let's see what's going on here. Free body diagram will show me the following. Okay. I have 200 newtons. And right here, 100 newtons. I have 2 meters here, 3 meters between those forces. And I have AY, BY, BX, okay, BX. And it was given that, okay, I have the thickness of this beam is 0.2 meters. And of course, I didn't put it here, but let me put it here. I have the components of this force. So right here, I'm going to put just the components. Components are 600 sine 45. Right here, 600 cosine 45. And this is 3 meters, 2 meters, and 2 meters. Sounds good? This is the problem that I have. Okay. And now I have 3 unknowns. And pretty much for equilibrium equations, I'm looking for the value of the unknowns. Okay. What should be the support reaction so that this body is in equilibrium? Okay. So what I'm going to bring to the table? Well, I'm going to bring my equations of equilibrium. And what is the first equation of equilibrium that we can use? Sum of the force in X should be 0. And remember, to the right, positive. Now, sum of the force in X should be 0. Now we are talking about equilibrium, guys. We're not just summing the force as you did in the last homework. We're not just summing the moments. We want them to be 0. So sum of the force in X should be 0. What do we have in X? In X, if you agree, we have positive 600 cosine 45 and positive BX. Bruno, why are they positives? Going to the right, going to the right. Okay, by my calculation here, BX is going to be negative 424.26 newtons. Bruno, I got a negative value. What does it mean? When you get a negative value for reactions, it means that the direction that you consider is wrong, is the opposite direction. Meaning that BX is not acting to the right. BX is acting to the left. Okay. And what is, if it's going to the left, what is the value? The value is 424 newtons. Going to the left. That's the only reason why you got negative. Negative just means the direction is wrong. Okay? The direction is wrong. Bruno, it is a problem to have the direction wrong? No. Because those are assumptions. Okay, we don't know. We want to calculate. Okay, if you got a negative, okay, all good. If first you consider going to the right and the answer is going to the left, you got a negative, you're correct. Okay, now if you got just a positive here, then you had a mistake, because you assume going to the right, and it's not going to the right, it's going to the left. Bruno, how I'm sure that this is going to the left? Well, take a look at these four other forces that we have. 645, cosine of 45. This is pushing our beam to the right. But to maintain the equilibrium, what the pin connection at B has to do? Fight back, push to the left. So this is going to the left. Okay, this is going to the left for sure. Okay. All right, so next equation of equilibrium. Sum of the force in Y should be 0. We know that go up is positive. Let's see what we have. AY going up. I don't know. Positive AY. Negative 600 sine 45. Negative 100. Negative 200. And positive BY equal to 0. Okay? What are we going to have? AY negative 424.26, negative 100, negative 200 plus BY. At the end, AY plus BY 724.26. Okay? So right now I cannot solve. I have an equation. AY plus BY 724. All right. Let's keep this right there. Okay. Let's move to the third equation. Okay, the new one here. Sum of the moments equal to 0. Moment where any point I can take the moment about A, about this, D. Okay, about B. Doesn't matter. Any point that you pick, you can take the moment. Okay. However, let me tell you, the best points to pick always is one of the reactions, where we have the reactions. Okay. In that case, or A or B. Bruno, why? Because let's take a moment about A. Once you take the moment about A, what is truly happening? Is AY doing any moment about A? Is AY doing any moment about A? No, it is not. Why? Because the point is here and the line of action is there. A is on top of line of action of AY. So no moment. So for this case, AY, no moment. So once we do this equation, okay, the others, we're going to have just BY. And then we're going to be able to come in here and solve. For example, let's talk about moment about B. Moment about B. Is BY doing any moment? No, because it's passing through B. Plus, is BX doing any moment about B? No, it's passing through B. And still, is 200 doing any moment about B? No, it's passing through B. Okay, so this B looks amazing. Okay, so no BY, no BX, no 200. Okay. But what is the most interesting point here? The most important one is by, no by. So we can have just ay, that is the other unknown that we don't know. Okay, of course, unknown that we don't know. But we can come back here later and solve it. Okay. And before I move, let me tell you that because the point is here and bx is also here, line of action of bx will not have moment about a as well. Okay, so I can put here bx. Okay. The line of action of bx passing through a. All right. So this one you could pick any of those 2 points. It's gonna work fine. Let me, because it's already here. Let me take the moment about b. Okay. Let me take the moment about b. It was the last one that I wrote. So for example, let's see, guys. This was the homework. Okay. Is ay doing moment about b? Yes. Moment about b? Yes. What is the length between the distance between line of action of ay to point b? All of these is 2, 3, 2, 5, 7. So it's ay times 7. Now, positive or negative moment, rotating about b clockwise, negative. Okay. Is 600 sine 45 doing any moment about b? Yes. Line of action to the point 5. 600 sine 45 times 5. Positive or negative? Counterclockwise. Positive. Is 600 cosine of 45 doing any moment about b? Yes. Because line of action is here, the point is down. And actually, sorry, this is not the thickness, it's just half point, 0.2 meters. Okay. I don't know if you can see here, but this is just half of it, 0.2 meters, half of it. Okay. So this is going to be 600 cosine 45 times 0.2. Okay. Then positive or negative? Well, it's trying to rotate like this. This point B, rotate like this. Clockwise is negative. And my last one, 100, line of action to the point, 2 meters. Counterclockwise, positive 100 times 2. 100 times 2. Okay. Now we have to do this calculation. Let me do negative 7ay. Let me see if I have here. This is 600 sine 45 times 5. Positive 21.32, negative 84.85, and positive 200 equal to 0. Negative 7ay is positive 2,236.47 equal to 0. Ay is negative 2,200 divided by negative 7. Ay is 319.5 newtons. That's my answer. If I know that this is it, okay, I'll go back here, go back there, solve by equal to 404.76 newtons. Like this. Then, also forgot about this one. Then this is it. Okay, this is my problem. I found the reactions. So for those body, that being to be in equilibrium with those force, of course, okay, when those forces are acting, the support reaction AY should be 319. The support reaction BY should be 404. And the support reaction X should be 424. Okay, and this is my problem. Okay, combining equilibrium equations, okay, and support reactions. Okay, combining the knowledge of moment that we discussed last week with equilibrium equations. Any questions? Any other questions? No? All good? I'm moving to the next problem. So let me put it like this if you are copying it or making notes. Okay? Okay. I have here, I think, 5 problems. So let's try to solve all of them. Again, guys, this topic will be in the midterm. Okay, so please, if you have questions, ask me. Okay, please ask me if you have questions throughout all the problems. Equilibrium of a rigid body. Starting example number 2. A crane has a mass of 1,000 kilograms. It's used to lift a 2,400 kilograms crate. Held in place by a pin at A, rocker at B, center of gravity at G. We need to find the components at A and B. Okay, the components of the reactions. Okay, great. Let me draw my free body diagram. Do this right here on the bottom. Free body diagram. I have something like this. Okay. Something like this. Come on, bro. Start again. Great. Okay, I have something like that. It was said that I have 1,000 kilograms is the mass of the crane. And as I said, the mass of the crane is the mass of the body. Okay, it's going to be applied at center of gravity, G. So right here, I don't have the mass of the crane. What I have the weight, okay, the weight of the crane. Okay, that's different. Let's already calculate this. 1,000 times 9.81. All right. Here, okay, this box is great. I don't have the mass of 2400. What I have is the weight of it. Okay, which is 2400 times 9.81. 23,544 newtons. All right. What else? Well, I know that this one here is 2 meters. This one here, 4 meters. And reactions. I have a pin at A. If it is a pin, okay, I have one reaction AX, another reaction AY. If B is a rocker, I have just one reaction BX. Bruno, why is not BY? Because even though it's one reaction, it's perpendicular to the surface. Okay, perpendicular to the surface. And this surface is vertical, so the reaction is horizontal reaction. Okay. So depend of the orientation of your support. Okay, keep in mind, depends of the orientation of your support. And this is 1.5 meters. All right. So this is my free body diagram. This is what we have. So let's start solving it. Let's bring the first equation of equilibrium. Sum of the force in X should be 0. Okay. Positive going to the right. Okay. Let me write this once again. What do we have? AX, BX, and well, that's it. AX, BX. At the end, AX is negative BX. I don't know. That's the only thing that I know so far. Let's go to the other one. Sum of the force in Y should be 0. Going up, positive. What I have? AY positive going up. Negative weight the crane. Negative W equal to 0. AY negative 9,000. Negative 23,000 to 0. At the end, this is straightforward. 33,354 newtons. All right, so I need to find AX, BX. Now, my third equation. Sum of the moments equal to 0 about any point. As I said, choose one of the point that we have reactions, AY or B or BY. So we can cancel it. Okay. A or B, in this case is AX, BX. That's what we are looking, right? AX or BX. All right. So just because it's easier to visualize here, let's take a moment about B. Okay. Moment about B. Let's go, guys. Moment about B. Is BX doing any moment? No. No BX. B is right here. Now my questions, please pay attention. Is AY doing any moment? No. Line of action is passing through the point. No moment about B. Is AX doing any moment? Yes, line of action is right there. Distance to the point is 1.5. So AX times 1.5. Now my question, positive or negative moment? Rotation around B is going to be clockwise, negative. Excuse me. The weight of the crane is doing any moment. Line of action here, distance 2 meters. So it's going to be 9,810 times 2 meters. Positive or negative? Clockwise, negative. Last one. They have space here. Negative 23,544 times. Why is negative? Clockwise times 2 plus 4, 6. This should be equal to 0. Okay. Do this calculation, go to the other side. You're going to find that AX is negative 10, 7, 107, sorry, 256 newtons. If this is it, Bx is the opposite. Opposite meaning positive. Those are my answers. Okay. So my AX is negative. What does it mean? It means that this is just the opposite. It's doing opposite. Okay. Bruno, I don't know if you guys are going to be able to visualize it. Let me try to do the same. Let's see if we can see those reactions. For example, if I had the weight, okay, let's say those 2 points here in my calculator, they are fixed. They are the pin and the roller, the rocker, okay? And applying the weight right here. So what's happened? You see that this is the wall. Once applied, take a look. What's happening? You see that on the top, it's trying to leave the wall. See that? So my force, my body is trying to, it's trying leaving. Wake up, guys, wake up. It's trying leaving the wall. So what should be my reaction? Well, my reaction here, I should keep this at the wall, fixed to the wall. So that's why AX is going to the left. It's trying to say like, hey, keep here. Hold. Okay? It's trying to hold it. As you can see, my movement is leaving, but my reaction is trying to, hey, come back. All right? Same for AY. What's happening with W? W is pushing down. You see, it's going down. AY is saying, hey, keep up. That's why it's going up. And BX, I don't know if you can see that, but once we rotate, okay, you can try to do it with your phone. You're gonna feel that this corner B is getting pressure, push it. Okay, so my structure is trying to go inside BX. Okay, creating some pressure. But BX, okay, the B is saying, hey, here now, go away, pushing back. Okay, so that's why it's positive going to the right. So see, you have some meaning. Okay, just doing like this exercise. We could do that without solving the problem. Okay, of course, we need to solve the problem to find the magnitude, but the directions we can have some idea already. Okay, and this kind of thing that I want you guys to think about. Okay, because in this class here we calculate reactions for supports. In future classes, you're going to design those supports. So you need to be able to find how much load is going to be on top of the reaction, on top of the support, in order for me to design that pin, design the blocker, design that column, design that wheel, that structure that is going to hold the structure, the other structure. Okay? So that's why I always say this class is the base for something bigger. Okay? That's why it's important to understand the basic. Okay? The basic, basic idea. Okay? That's the truth from this class. All right, so we still have time. Let's jump to another one. Okay? I'm jumping to problem number 3. Okay? And it's a different type of support that I want to cover here. Any questions? Please let me know if you have any questions. Okay. I'm starting number 3. The beam's fixed at the wall. So right here, we already know support. It's fixed at the wall. Determine the reactions caused by the support. Consider the beam has a mass of 100 kilograms. So we have a force, 1200 newtons. The beam is fixed. And also we have the mass of the beam, meaning we're going to have the weight of the beam. Okay. All right. So let's just analyze here the supports. If this is a fixed support, if you go back at lectures, the lecture here, you're going to find that the fixed support introduce 3 reactions. AX, in this case is AY, and also we have a moment reaction. I'm going to call MA. Okay, I call MA. 3 reactions, moment and 2 force reactions. Okay, cannot start the problem without considering the mass of the beam. Okay, so this is a regular shape. Regular shape, red is the center of gravity. In most of the cases, right here, the middle, we have this weight of the beam. Okay, let me draw the free body diagram. Let's visualize. We're going to have this beam right here. We're going to have AY, AX, MA. We have a force here, 1200 newtons, 2 meters. We're going to have this weight, which is going to be 100 times 9.81, which is going to be 981 newtons. And this is the distance, 3 meters. 3 meters. This is 2 meters right here. Simple. That's the force that I have. Just want to introduce to you the fixed support. So how we solve it? Sum of the force in X should be 0. What do we have in X, guys? Well, I only see AX. AX equals 0. So I have no reaction. Reaction is going to be 0. I don't have any other external force acting on the beam. Okay? Sum of the force in Y should be 0. What I have in Y? AY going up, positive. 1200 going down. And going down, 981. Equal to 0. But I have AY, once I calculate, 2081, 2181 newtons. And then what's going to be a little bit different is the moment about A. Some of the moments about A. Now question, is AY doing any moment about A? No. Okay, point A is here. Is AX doing any moment about A? No. Okay. What about moment A? Is moment A doing any moment at A? Yes. Yes. It's a moment. It's rotating that body. Remember what we call this as a concentrate moment? Okay. This sign here. Okay. It's already a moment. Okay. And moment has no distance. Moment is rotating that point. So that is moment. The way that I wrote, that I draw it, is counterclockwise. Counterclockwise is positive MA. It's my moment reaction. Okay. What about 1200? Yes, 1200 times 2. About A is doing clockwise, negative. And negative 981 times 3. I'll find my moment A is 5,343 newtons meter. Okay? It means no reaction X, Y, positive 281, 2181, going up because it's positive. And moment A is my reaction, counterclockwise, 5,343. Okay? So those two other forces is fixed here. I have no rotation. Those two other forces are trying to rotate. Okay? You can see, trying to move my hand here clockwise, trying to rotate this. But this is fixed. I will not allow it to rotate. So what I'm gonna do? The moment, when I'm gonna do a moment, rotating it counterclockwise. And how much is this moment? 5,343 Newton meters. Sounds good? Sounds good, sounds good, sounds good. Any questions? Questions? Okay. All right. Problem number 4. Let's keep going. Okay. A lot of problems here I want to bring today, so you get all different case scenarios to get ready for exam, homework as well. Okay. Different problems that we can find in real life. For example, this one's a new one, a little bit different. The L-shaped body is supported by the roller at B. Look, what do we have? B over there is inclined. And we have a pin at A, pin support. We have 200 pounds vertical force at C and 500 pounds foot couple moment. So see, we have a couple moment over there. Okay, and we already discussed couple moment. Find the reaction at A and B. A and B. Okay, I start. Just giving time if you're copying it. All right. Okay, guys, so let's discuss first the problem, the reactions. Okay. First, A is a pin. Pin. Let me do another color because the colors are red for the external force. So let me use blue. AY. AX. Okay. Pin support. AY. AY. AX. Now B is just roller, but take a look. The roller is inclined. And where is the reaction of the roller? The reaction is perpendicular to the surface, meaning let's say this reaction B. My reaction B, okay, not X, not Y, because it's inclined. My reaction B is inclined. Okay. And how I should solve a problem like that? When my equations are sum of the force in X, sum of the force in Y, sum of the moments. Same way that we have been treating when we have a force that is inclined. What do we need to find here, guys? What do we need to find? We need to find components. Bruno, but components of reactions? Yes. If the reaction is inclined, in order for me to solve the equations of equilibrium, I need to find the components of those reactions. Okay. So I need to find which one is going to be B cosine and B sine. And this, the way that the problem is setting here with the angle is a little bit tricky, but let's see if we can get it through. Okay. To visualize. Sometimes it's easier to visualize the angle. Which one is going to be sine, which one is going to be cosine. Okay. So what I'm going to do is the following. This is a little bit tricky. Let me explain to you. Take a look. This is X, this is Y. Okay. You can do the following. You can have this cut, X is cut, at the same inclination as this guy here. Meaning that if you agree, okay, this 60-degree, by the way, is this angle here. Okay, I think it's not that clear, but this angle is 60 degrees. So, let me put the other pink one. Pink, 6 degrees. So the 60 degrees is right here. Okay. Where's my B? My B is right here. If this is 60 degrees, this is 60 degrees. This is 60 degrees. And this is 60 degrees. How you know that? Complementary angles, 30 degrees, then this is 9 degrees, 30 degrees, 30 degrees, 30 degrees, 30 degrees. Okay. And why are you doing that, Bruno? Just to show you a trick way. Okay, there are other ways I'm going to show in a moment. But for example, this is the X component, and this is the Y component of B. Now you can see that vector, its component, now you can see this one is going to be B, cosine. This one is going to be B sine. Okay? Because we are talking about vector and component, 60 degrees. So this is cosine of 60. This is sine of 60. Okay? Or we can think about just very simple here. Maybe I complicate so much. As you can see there, that triangle, where there this is 60. See? If you think about this as the y component and this as the x component, okay? Actually not. Actually, you cannot do that. Because y is going to be the cosine. And cosine opposite cosine adjacent. Sine is the opposite. Just the configuration of that triangle should be the other way around. But if you do this one here, that's what I always do, and not get confused. Okay? Not get confused. Because the 60 degrees is truly between those two here. Okay? 60 degrees. Okay? So this is the best way to visualize it. All right. So we know that one is B. Now one is B cosine. Another one is B sine. Okay, and pay attention, I'm not write bx sine, by cosine, because they're coming from B. Okay? Just one reaction. Just have one value. The resultant is B. Okay, so B cosine, B sine. B cosine, B sine. Should I draw the free body diagram here? Just for the sake to draw, I already draw everything over there. Okay, so right here, what do we have now? We have B sine, B cosine. 3. Then we have 250. And then 4. And then 1.5. And 1.5. We have AX, AY. And then finally, almost forgot, concentrate moment of 500 pounds foot. Okay, that's everything that I have. So let's calculate here. Let me see if I can put it here. Sum of the force in X should be 0. What I have in X? I have positive B sine, positive AX equal to 0. Well, right now, I cannot solve this equation. So let me go to the other one. Sum of the force in Y. I have B cosine positive. I have negative 250. And I have positive AY equal to 0. Okay. Right now, I cannot solve it. I don't know B, I don't know AY. Okay. So let's go if the third equation can help me. Sum the moments about a point. Which point? Well, if I take moment about, take a look. If I take moment about B, this is not going to have moment, this is not going to have moment. But AX and AY will cause moment about B. Okay, because this is line of action, this is line of action. So I'm going to have two unknowns. Not going to be able to solve it. Then I have a system of equation. However, if I take the moment about A, AX and AYs, they are not going to cause any moment. And those two, they are just B, B. So I can find B over there. So I'm gonna take the moment about A. Take the moment about A, see if you guys agree. B sine 60 degrees times 3. And take a look, guys. This is not this 3. Okay? B sine, this is this 3. This distance 3 here. Okay? 1.5 plus 1.5. Then clockwise, negative. B cosine times 7. B cosine times 7. Line of action to the point 7. Clockwise, negative. 250 times 4. Oh, I already put the positive, but counterclockwise. Okay? And then we cannot forget about moment. Couple moment. Remember, couple moment is already rotating the body. Rotating where? Counterclockwise. So this is a positive 500. No distance. Why? Because already a moment. Already a moment. Already a moment. Okay? Already a moment. And then AX and AY, no moment at all. Okay? So this is it. Okay? Once you calculate this, sum B together, blah, blah, you're gonna get B equal to 245.9 pounds. Okay? Try to do this calculation here, guys. Try to do this calculation. You have two B's, you have use some B's, and then go to the other side, divide. Okay, see if you can get this value. With that, of course, we come here, solve. We're gonna find AY equal to 127.05. And then we go back there and solve as well. We're gonna find AX negative 213 pounds. Okay? So the only thing here is AX should be going to this way, to this way. Okay? Again, I skip the calculation. Please do the calculation by yourself. See if you can get the answers. Okay? That's important, guys. That's important. Okay, so this B that I found is truly the reaction B, right here. Okay, B sine, B cosine are just the components of that reaction. So right here I have 245.9. Okay, 245.9. All good? Any questions? Any questions? Okay. Okay, moving. Problem number 5. Okay. Problem number 5. A procedure to evaluate the strength of a triceps muscle. A person pushes down on a load cell with a palm of his hand as indicated in the figure. If the load cell reads 160 newtons, determine the vertical tensile force F generated by the triceps muscle. The mass of the lower arm is 1.5 kilograms, with mass center as G. At G. Okay, so we have I want to find the vertical tensile force F, triceps. What is the triceps? The triceps is right here. Okay, so let's assume an assumption here. Let's assume this force is what? Body here is 90 degrees. Okay, was not giving any um, orientation. So let's assume, first assumption, let's assume this is 9 degrees. Okay, so we have just this vertical force in the triceps. Okay, 9 degrees. What else? We have the weight here. We talk about weight of the lower arm at G. And we have this loading cell rating as 160 newtons. Okay, this is a force. Okay, this is a support. Okay, this is a little bit different. This is a support. Applying the force, that is a support. So we know that this we have going down is like a normal, okay? Like a normal. It's resting on the ground. It's a normal S 160 newtons. Okay, we have this normal force. Okay, so this is my my loads that I have. So let's find the free body diagram. Take a little bit of this noise, take out, remove this noise. So let's take a moment about O. Well, let's consider this O because all the dimensions are going to the O. So this is O. And first we have a force F that I want to find. Uh, let's say millimeters. So let me move to meters. 0.025 meters. Right here I have 0.15 G, and right here 0.15 for that one. This is W. This is going up 160 newtons. This is meters, meters. And then my last thing to do is calculate his weight, which was 1.5 kilogram times 9.81. 14.7 newtons. Okay? Very simple problem here, but different aspect. Okay, we are talking about here, especially for the biomeds. Okay, biomeds engineering. You're gonna work with those kind of problems, of course, more advanced problems, but starting from here. Okay, I like this problem here. Okay, so what we have, sum of the force in X should be 0. Okay, in this case, no X force. Okay, there's no X force. We don't know. Okay, we can have here the triceps causing some X force, but we're not considering it here. Sum of the force in Y, we have the F going up negative 14.7, and we have also this, actually before that, think this would be, I should do the moment. This is a trick question. Should think about more about this one now. I'm thinking about, okay, because this is what we don't have the rotation, okay, is regarding the rotation that we are talking about point O, moment about O, because then we have to assume other things here in order for this specific um, specific here when once you do the sum of the force and Y. But what how I want to solve it the moment about O. So just going straight to the moment about O and need to think about the sum of the force in X. But let's do the moment about O, then I can probably figure it out a little bit more about this Y, the assumptions that we have to make in Y. But in moment about O, that's how I want to solve this force, okay, because there are a lot of assumptions here, because it's a more advanced problem for other muscles. But this is moment about O should be 0. And then, yeah, and then I have my 160 force, okay, positive times 0.3. I have my negative 14.7 times 15, okay, 0.15. And also I have my force, okay, negative 0.025. Okay, this for the force acting on the triceps. Okay, I forgot to mention that we have the bone here as well. Okay, and of course we're gonna have some force here at the bone. Force bone. Okay, but for the assumption here that we want to find just the force on the triceps, that's what I forgot. Sorry about that. Okay, force about the bone. Okay. But because I want to find the force on the triceps only for this problem, okay, that would be some of the force about O, where the bone is. Okay, so that's the what I forgot. I'm sorry about that. Okay, so this should be 0. Okay, so let's go again. Let's take a step back. Okay, my mistake here. Okay, we have the force um, of the triceps. We have the force at the bone as well. Okay, the force at the bone, and we have the W, the weight. Okay, and we have this force here pushing this loading cell. Okay, with that in mind, take the moment about O and YO, because we don't want to know about the force at bone. The question is just asking the force at the triceps. So for a moment about O, there is no moment caused by the bone. Okay, then I can come here and solve this problem here. So let me solve it together. 160.0.3 is going to be, okay, now I see some light, 48. This is 14.7 times 0.15. This is 2.205. Okay, and this is negative 0.025 F. This is 48 minus that, 45. Go to the other side. F is 45,795 divided by 0.025. Okay, now I see the answer. F is 1083, 1.8. Okay, newtons. That's the answer. That's the force on the triceps. Okay, so I have the force on the triceps, 1831.8 newtons. Okay, that's the force I was looking for. All right, so this is causing just solving the equation regarding the moment. Okay, moment about O, and then I can calculate the triceps. Okay, so some of the times, okay, in this case, okay, for this specific case, some of them we're gonna just be able to solve using the moment. Here I just could come and solve the moment. Okay, some of the problems we needed the three full equations, okay, because we have others to find. Okay, so always a good problem to visualize other different aspects, okay, of the of different problems. Okay, but here once again, simple problem, just distance, distance, okay, and force, and be able to do what? To do the moment, okay? I think the most important is moment, okay? Since last week, moment is very important, all right? So this is this problem, okay? Problem number 5. And then any questions? And then we have another question, another problem to finish the class today, okay? To finish the class today, which is problem number 6, and also a little bit different. We're talking about airplane, and the way that the problem, I took these problems from the book, asking for a little bit, a little thing different, just a little thing more. I'm gonna do it, but the reality, what I want you to be able to find is the reactions. Okay, find the reaction that I want you to be able to find the reaction. Okay, so let's go for the last problem. We have time. During giant tests on the ground, a propeller thrust of 3,000 newtons generate on this 1,800 kilograms airplane, mass center at G. The main wheels at B are locked, do not squeak. So, sorry, with that information, I know BY, BX. The small tail wheel at A has no brake. So no brake meaning just that support is free to move with no brake, AY. Compute, then what they ask is a little bit different, but what I want to know is those reactions. Then later I'm going to solve, as the book said, compute the percentage change and in normal force A and B as compared with the engine off values. Okay, meaning let's do two cases. One case where we have T acting, another case where the engine is off, meaning I have no T, just the airplane by itself. Okay, how much should be that reaction? And once the airplane, once we have this T, okay, how much is going to be those reactions? That's it. Two cases, off and on. Engine off, engine on. Okay, so let me start with engine off. Little bit easy. Okay, engine off. Okay, engine off. How should be my problem? Okay, my problem should be something like very simple, like this. Okay, I have the airplane like this. Let's put just this line here, the airplane, and let's say I have this here as my wheel. Okay, like this, and this is my other wheel, like this. Okay, wheel, and this wheel. Okay, something like that. And what I have AY, I have BY, and the wheel, I have BX. Right here, I have this G. That's the weight. All right. And that's it. What are those distance? From here to W, I have 4. W to this, I have 0.8. Okay. And if needed, this distance here, up to there, is 1.4 meters. Okay. Now for the engine off, that's it. I don't have T. Okay, so let me reduce this one actually. I don't have T. And with the engine off, of course, let's calculate this W and put it here. W is 18. So W is going to be 18,000, 9.81. 18,000, 9.81. 17,658. Okay, that's the weight. So coming, should I do it side by side? Oh, it's okay if I do it here. Sum of the force in X should be 0. Okay. What I have next for this this first one, Bx equals 0. So no reaction at all. Okay. And what I have in Y, okay, Y is going to be AY plus BY negative W, okay, AY plus BY 17,658, and then some of the moment about A, the moment about A, W is going to be negative, so negative 17,658 times 4, and then positive BY times 4.8, okay, 4.8. All the distance to point A. How much is it? Let me calculate this. 17,658 times 4 divided by 4.8. This is going to be BY. 14,715. This is pounds. Newtons, sorry, newtons. Newtons. AY, if this is 14, this is 17,658. 2,943 newtons. All right. So this is when the engine is off. Okay. The engine is off. Let's see now when the engine is on. What do we have? The same airplane is W here, the same AY. So the engine is on. Equilibrium is about to move, So let's see how much are those force about to move. Okay, and then right here, he gave me T. This is 12 degrees. Of 3,000? 3,000. 3,000 newtons. All right. Good, guys? Well, here, as you can see, okay, 12 degrees, and fix it, is inclined. So what are we gonna have? T cosine 12, T sine 12. Okay? T cosine 12, T sine 12. That's the components. Now, we have some assumption here. Not assumption, but you need to understand one thing for this specific problem, so that's why I put it here. Okay? Of course, before that, sum of the force in x equal to 0. Now we have bx, okay? Bx, t cosine 12 minus bx equals 0. So bx is going to be the t cosine 12. T is 3000, 3000 cosine 12, 2934, 44 newtons. Okay, easy. All right. Here, same. Sum of the force in y, ay plus by, negative 17,658, and positive t sine 12. This at the end should be the following: 17,658 minus 3000 sine 12. This would be 17,034.26. Okay. Cannot solve. Now I have to go to moment. Moment about a point. Moment about a point. Now, guys, this is the thing here. Okay. When you take a look at this one here, okay, this problem right here, you see this t, and you see that the distance that was given to you is 1.4. Okay, 1.4 only. Now the thing is the following: you have the option, of course, have the option. Consider this force acting here, force T. Okay, and what do you have to do now? You have to find all this distance here, meaning what is missing from this 1.5, 1.4, and also this whole distance here. What is missing from the wheel to that part on the front. Okay, you can do that. You can find those distance because components here, components there. However, let me tell you the following. Okay, however, this force T, okay, any force that you can see, okay, any force that you can see, what happened? This T is applied at this line of action, right? This line of action. This line of action. Meaning, okay, that you can move this T all around this line of action. Meaning you could put this T acting since in here, since there, and have its components right here and right here. You could have this T all the way to here and have components acting here and there. You could have all the T all the way to here and have components acting here and there. And Bruni, this is going to work? Yes. Because now the distance from each one of those components, they're going to change. Okay? And if you try to test it later, okay? Try to find this distance here, this distance there, okay? You're going to see that you're going to get the same answer. So what I'm telling you is the following. This T, okay, I'm going to move this T to point G. Okay, meaning that this force is coming all the way here. Excuse me. And then its components, okay, I'm going to translate. Okay, so this is equivalent as this one here that I'm going to draw. T sine, T cosine, W, By, Bx, Ay. Okay? So this is what I'm going to consider here. And again, why I'm doing that? I'm doing that because easily I know those distance. This distance is 4, this distance is 0.8, and also I know this distance here is 1.4. Okay? So that's why I'm moving it. Okay? And again, guys, if you calculate this distance here, that distance, and the distance that is missing here, and you do the same calculation of moment about A, you should get the same answer. Okay? That's the beauty. Okay? So just because the time is almost done, let me just finalize this one here. Okay? And finalize by doing the following. Sum the moments about A. I have negative 17,658 times 4. Okay? What else? And put this first. By times 4.8. What else? Take a look. Plus T sine of 12 times 4. Okay? And negative T cosine 12 times 1.4 should be 0. Okay? So if I do all of this, let me calculate this with you. By can go to the other side, other one goes to the other side. So let me do 17,658 times 4. Then T, which is 3,000, sine 12 times 4. Then 3,000 cosine 12 times 1.4. Now my by should be this one, so it's going to be by is going to be 6402884, something like that, divided by 4.8. This should be by of 13,339.34. Okay, let me check because it's different from my answer. 1.4. Can anyone check, see if it's correct? If I miss up something here? 1,000 sine of 12 is correct. Maybe it was my notes. Times 4 plus. Oh, I mess up here. I put a plus here, but it's negative. This is negative. Sorry about that. So this one should be something else. This one should be something else. So let me start again. 17,658 times 4. That's what I did. Then sine 3,000 sine 12 times 4. Okay, then 3000 cosine 12 times. Okay, now I got the same. 72, 245, 28 divided by 4.8. Okay, now that's it. Found my mistake. 0.1 newtons. AY in this case should be 15 minus the 17,034.26. This should be 1983.16 newtons. All right, so that's it. Okay, so the difference between them, okay, AY, BY, AY, BY, AY, okay. One is engine off, engine on. As you can see, they're going to be, BY is going to increase, AY is going to decrease. So that's the percentage that what it was asked. Okay, I'm not going to calculate this, forget about this. I want to just stop here, AY, BY, AY, BY, for two different cases. Okay, so that's it. Any questions? Any questions at all? Questions, guys? Any questions regarding those problems? Okay, so today I use all the hours that I had in order to solve as much problems, different problems as possible. 6 problems that we solve, okay, with a few assumptions in some of them, some straightforward calculation in others, okay. And this is a really important topic for life, okay, for life as engineering, equilibrium equations of a rigid body, okay. All right, so if you don't have questions, I'll stop here. Okay, it's already time. I will see you tomorrow, so keep an eye open for the test, the fake midterm, and also please try to work on the homework number 3, at least the first, I think, 4 questions right now during this week. You can ask me questions, make me the questions, because this is going to be in the test. Okay, guys, take care. See you tomorrow.
Thank you.
Thank you.